Welcome to a tutorial solving a problem of thermodynamics and heat transfer with Simcenter Amesim Student Edition. The problem statement displayed is seeking to evaluate the heat transfer through an exterior wall of the listed dimensions on the 4th of July in Atlanta, Georgia from sunrise to sunset. The wall will experience heat from the sun on the outside and a constant temperature of 72 degrees Fahrenheit for the interior. After this two-part tutorial, you should be able to utilize the thermal library to simulate heat transfer methods, how to establish materials for thermal simulations, and how to impose real environmental conditions with the thermal library. This tutorial will be broken into two parts, with this video being part 2, which will simulate the heat transfer through the wall with insulation. The link for the first video is in the description and explains in detail how the model to start here was created. The Amesim model is the same as what was left at the end of part 1, with the same components and parameters. To easily compare the behaviors of this thermal wall with and without simulation, let's copy the model by highlighting it and pressing Ctrl+C. Next, unselect the model and press Ctrl+V within the sketch window to paste the second copy of the model for easy comparison. With the two models available now, some adjustments can be made to clean up the sketch. Walking through the changes completed, the signal logic for the temperature of the surroundings depending on the time of day has been set to be sent to both models with the form of dynamic transmitters and receivers. The dynamic transmitter attached to the output of the temperature logic above will send the same value to each of the receivers set to it, which are both set to input a signal to the newly added supercomponents. Because the sun's radiation and convection behavior are not of priority for analysis, the components were compiled and placed into a supercomponent, created and saved into a library through the supercomponent tutorials whose links are also in the bio. Opening up either, you can see those heat transfer components within that still have the same parameters. More additions are labels for each of the models to differentiate which thermal wall component will include insulation. The last addition must be made to add a thermal solid properties component for the insulation. Once added, we can move to submodel mode. First, assigning the submodel for the new thermal solid properties component can be done with Premier Submodel. Before moving to parameter mode, we need to set the port tags for the transmitters and receivers. The port tags determine what transmitters interact with what receivers. And right-clicking on any of them, and then opening the port tag submenu, and then opening the port tag list will open a pop-up displaying all applicable components within the sketch. The value to set the relationship must be entered into the port tag column, and because all the components listed are interacting with each other, the same value can be entered for all, and any value is acceptable. From here, press close and move to parameter mode. To begin parameterizing the model, let's establish the parameters for the material definition for the insulation. A standard insulation used for an exterior wall with a 2x6 frame is R19, which is made from fiberglass. The 19 in the name is the insulation's R value, which corresponds to the material's thermal conductive resistance. This R value is determined by the thickness of the insulation divided by the thermal conductivity of the material. Using the known thickness of the insulation, being what was the space filled with air from the initial model, and the R value of 19, the thermal conductivity for the material can be calculated utilizing post-processing. Back in Amesim, the post-processing window below contains the layer 2 thickness value of 5.5 inches. The following line has the expression to determine R19 insulation's thermal conductance, being that thickness converted to feet divided by 19, then multiplied by the conversion factor for a value in watts per meter Kelvin. This value can be copied into the respective field for the thermal definition component representing insulation. The values for density and specific heat are already entered, which can be found through research. And now let's move to the wall component to reflect that with insulation within it. The changes needed begin with changing the type of wall to 3 layers, but with them being material, 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 rather than material, air, material. The The icon of the component will change to show the error being absent. Next, open the definitions linked with the materials parameter section and assign the solid index type for layer 2 to be 3 to reflect the insulation material component. With that done, let's move to simulation mode and rerun the simulation. After running a simulation across the same time as the previous demonstration for thermal walls, graphs for the temperatures of both the external and internal sides of both walls show how insulation is able to maintain the interior temperature while also causing less heat flow from the outside, and in turn heating the exterior side of the wall further than without insulation. And with those results available, this demonstration is concluded. Thank you.